People have secrets. That's just how it is. We want to keep some things private. Maybe it's a love letter, maybe it's a military plan, maybe it's our bank details. For as long as people have had secrets, they've wanted ways to protect them. This is where codes come in. We try to hide our messages, we scramble them up so only the right person can read them. And for just as long, other people have tried to read those hidden messages. They try to break the codes. This creates a constant fight. It's a game of hide and seek that never ends. The big question is, can we make a code that absolutely no one can ever break? A truly unbreakable code? It sounds nice, doesn't it? Something completely safe. Something that protects our secrets forever. But is that even possible? It's a simple question with a very complex answer. Most people think of a code as just a tricky puzzle, but it's much more than that. It's math, it's technology, it's human behavior, and it's constant change. First, we need to think about what unbreakable even means. Does it mean it's just very hard to break? Like, it would take a supercomputer 1,000 years? Or does it mean it's impossible to break no matter how much time or computing power you have? These are two very different ideas. Most codes we use today are in the first group. They are very hard to break. They are computationally difficult. We rely on the idea that it would take so long to break them that the secret they protect would be useless by then. But impossible is a much stronger word. It means there is no path, no method, no amount of effort that could ever reveal the secret. That's a high bar. Let's look back in time a bit. Codes are not new. People have been using them for thousands of years. And Julius Caesar used a simple code. He would just shift each letter of a message a few places down the alphabet. So might become DB, might become E, and so on. This was called a Caesar cipher. It was good enough for his time. Most people couldn't read anyway. And if they could, they wouldn't expect to shift a message. But today, this code is a joke. It's incredibly easy to break. How do you break a Caesar cipher? You just try every possible shift. There are only 25 possibilities, or you look at the letters. In English, some letters are used much more often than others. He is very common. T is common, percent is rare. If you see one letter appearing over and over in a coded message, it's probably. This is called frequency analysis. It's a very old method. It became a powerful tool for code breakers. And it showed that simple substitution ciphers, where one letter always stands for another, have a fatal flaw. They leave patterns, so code makers got smarter. They thought, what if we don't always use the same shift? This led to codes like the Vigenère cipher. It used a keyword. Each letter of the keyword would tell you how much to shift the letters in your message. If your keyword was cat, the first letter of your message would be shifted by C3 places, the second by a 0 places, the third by T19 places, the fourth by C again, and so on. This seemed much harder. The same letter in the original message might become different letters in the coded message. This confused frequency analysis. It was considered very strong for a long time. People even called it le chiffre indecipherable, the unbreakable cipher, but it wasn't unbreakable. Eventually, people found ways to break it. They realized that if the keyword was repeated, there were still patterns. You could find the length of the keyword. Once you knew the keyword length, you could break the message into smaller parts. Each part would essentially be a Caesar cipher. Then you could use frequency analysis again. This showed an important lesson. Even if a code looks very complicated, if there's any pattern, any repeatable element, a clever code breaker might find it. As the world got more connected, the need for stronger codes grew. Governments, militaries, and businesses needed to protect information. World War I. And I saw huge advances in coding and code breaking. Machines started to get involved. The most famous example is probably the Enigma machine used by the Germans in World War II. It was a complex electromechanical device. It used rotors that spun and changed the way letters were scrambled. The settings of the rotors changed every day. It produced incredibly complex substitutions. It seemed incredibly secure. Breaking Enigma was a monumental task. It wasn't just about math. It was about finding human weaknesses. The British code breakers at Bletchley Park, led by people like Alan Turing, didn't just smash the math. They found mistakes in how the Germans used Enigma. For example, some operators always started their messages with the same letters, like MGM for Meteorologischer Großraum mit Central Weather Region. Or they would type the same message twice, but with different settings. These small operational errors gave the codebreakers tiny footholds. And they built early computers, called bombs, to systematically test Enigma settings. They used traffic analysis, they captured codebooks. It was a mix of brilliant minds, new technology, and human error. Enigma was broken. It was very, very hard. But it wasn't unbreakable, and its breaking changed the course of the war. After the war, computers became more powerful. This changed the game entirely. Now codes could be incredibly complex. They could do calculations in seconds that would take human centuries. Modern cryptography began. A big leap came in the 1970s with public key cryptography. This was a revolutionary idea. Before this, if you wanted to send a secret message, you and the receiver both needed the same secret key. You had to find a way to share that key without anyone else getting it. This was a huge problem. How do you share the key secretly in the first place? Public key cryptography solved this. It uses two keys. One key is public. You can give it to anyone. It's like a padlock that anyone can use to lock a box. The other key is private. Only you have it. It's the only key that can open that specific padlock. So, if I want to send you a secret message, I use your public key to encrypt it. Then I lock it with your public padlock. Once it's locked, only you, with your private key, can unlock it and read it. This is amazing. We don't need to share a secret key beforehand. The most famous public key system is RSA, named after its inventors Rivas, Shamir, and Adelman. RSA and similar systems work because of very hard math problems. They rely on things like factoring very large numbers. It's easy to multiply two large prime numbers together to get an even bigger number. But if you're only given that very big number, it's extremely hard to figure out which two prime numbers were multiplied to make it. This is a one-way function, easy to do one way, very hard to reverse. Our current computers just aren't fast enough to factor these huge numbers in any reasonable time. This is why we say these codes are computationally secure. It's not impossible to break them. It would just take longer than the age of the universe with today's technology. So, for all practical purposes, they are secure. For now. But this brings us back to our definition of unbreakable. If unbreakable means impossible no matter what, then RSA and its cousins don't fit. They are just very, very hard. And very, very hard can change. Computers get faster. New math discoveries happen. What takes 1,000 years today might take 100 years tomorrow or a year next decade. This is the constant arms race. Codemakers try to stay ahead. Codebreakers try to catch up. Is there anything that is truly unbreakable? Theoretically, yes. There's something called a one-time pad. It produces a coded message that is totally random. Every possible original message is equally likely to have produced that coded message. There are no patterns, no amount of computing power, no amount of time, no clever math can break it. If you intercept a message encrypted with a perfect one-time pad, you simply cannot tell what the original message was. It's information theoretically secure. This is the closest we get to truly unbreakable. And that key needs to be as long as the message. How do you share a truly random, super long key with someone else secretly and before you send the message? This is a massive headache. If you send the key over an insecure channel, it could be intercepted, and then your future messages are not secure. Managing this is incredibly difficult for everyday communication. Because of these practical challenges, one-time pads are rarely used for general communication. They are used in very specific high-security situations where key distribution can be handled physically and securely, like in diplomatic hotlines or for some military communications where keys are hand-delivered. But for your online banking, your emails, or your phone calls, it's just not feasible. The one-time pad shows us what unbreakable means in its purest sense, but it also shows why it's so hard to achieve in the real world. Even if the underlying math of a code is strong, even if it's computationally very difficult to break, codes can still fail. They often fail in ways that have nothing to do with the math itself. These are practical weaknesses. One of the biggest practical weaknesses is humans. People are often the weakest link in any security system. No matter how strong the code, if a person lets the secret key out, the code is useless. Another weakness is implementation flaws. Cryptography is incredibly complex to build. Developers write software that uses these algorithms. Sometimes there are bugs in the code. A small mistake in the programming can create a backdoor or a weakness that a clever attacker can exploit. This isn't about breaking the math, but about breaking the system that uses the math. An example might be a random number generator that isn't truly random, making the keys predictable. Or an error in how the encryption process is chained together. These flaws are often found years after the software is released. Then there are side channel attacks. This is a fascinating area. Instead of trying to crack the code by doing math, attackers try to gain information by observing the system that's running the code. If it takes slightly longer for certain inputs, that tiny difference might reveal something about the secret key. By precisely measuring these tiny fluctuations, attackers can sometimes deduce parts of the key. These sounds can reveal information. Electromagnetic radiation. Electronic devices emit electromagnetic waves. Analyzing these emissions can sometimes give away secrets. Cache attacks modern processors use memory caches to speed things up. By observing how a cryptographic program uses the cache, an attacker can learn things about the key. These attacks don't break the code's math, they exploit the physical reality of how the code runs on a machine. This means even a theoretically strong algorithm can be vulnerable in practice. Governments also sometimes demand backdoors in encryption software. A backdoor is a secret way for a specific entity, usually the government, to bypass the encryption. If such a backdoor exists, it creates a vulnerability that could be exploited by anyone who discovers it, not just the intended government agency. This makes the code fundamentally weaker for everyone. The existence of these practical weaknesses means that even if we had a perfect, computationally unbreakable algorithm, its real-world implementation would still be vulnerable. It's like having the strongest lock in the world but putting on a door with paper-thin walls or leaving the key under the doormat. The constant struggle between code makers and code breakers is often called an arms race. One side develops a new, stronger code, the other side develops a new way to break it. This pushes code makers to invent even stronger methods. It's a continuous cycle. Cryptography is not a solved problem. It's an active field of research. New algorithms are developed. Old ones are refined or found to be weak. New attack methods are constantly being discovered. Right now, a huge new challenge is on the horizon: quantum computing. This isn't just about computers getting faster. Quantum computers use the strange rules of quantum mechanics to perform certain calculations in ways that classical computers cannot. They don't just speed up existing processes, they offer fundamentally different ways to solve problems. And this is a big problem for much of our current encryption. Many of the public key systems we rely on today, like RSA, depend on problems that are hard for classical computers, like factoring large numbers. But quantum computers, specifically using an algorithm called Shor's algorithm, can solve these problems very, very quickly. If a large-scale, stable quantum computer is ever built, it would instantly break much of the encryption that secures our internet today. This is not a theoretical threat for the distant future. It's something cryptographers are working on right now. Because of this, a new field called post-quantum cryptography has emerged. Researchers are trying to develop new cryptographic algorithms that are resistant to attacks from quantum computers. They are looking for new math problems that even quantum computers find hard to solve. The goal is to have these new algorithms ready and implemented before powerful quantum computers become a reality. But are these new post-quantum codes truly unbreakable? Or are they just harder for quantum computers to break? And what if a new quantum algorithm is discovered that can break those? The arms race continues, just on a new battlefield. So, let's come back to the main question. Can we create a truly unbreakable code? Theoretically, yes. The one-time pad is truly unbreakable in an information theoretic sense. But its practical limitations make it unusable for most modern communication. It needs perfect secret key distribution and management, which is almost impossible to achieve at scale. Practically for general use, no, not in the absolute sense, but one. Computational strength is relative. What is computationally impossible today might be feasible tomorrow as computers get faster and new algorithms are discovered. The definition of too long to break keeps changing too. Human factor, people make mistakes. They choose weak passwords, they lose keys, they fall for social engineering. Humans are the biggest vulnerability. These attacks don't break the math, but the execution of the code. 5. New technologies. Quantum computing is the latest example of a disruptive technology that could render current strong codes useless. There could be others we haven't even imagined yet. 6. The arms race cryptography is a moving target. There is no final victory, there are only temporary advantages. What we usually mean by unbreakable in the real world is practically unbreakable. This means the code is so strong that it would take an attacker an unfeasible amount of time, money, or resources to break it using currently known methods. The secret will either expire before it can be broken, or the cost of breaking it would far outweigh the value of the secret. This is the goal of modern cryptography. It is about making it hard enough. Hard enough to protect your bank account from a casual thief. Hard enough to protect government secrets from rival nations for a reasonable period. It's about risk management, not absolute invincibility. We aim for extreme resilience, not for ultimate vulnerability. We try to build codes that can withstand known attacks and adapt to new ones. We design systems that are robust, even when there are minor flaws. We understand that security is a process, not a product, It needs constant vigilance, updates, and research. So no, we probably cannot create a truly, absolutely forever unbreakable code for all our general communication needs. Not if unbreakable means impervious to every possible future attack, every human error, and every technological advancement. The closest we get, the one-time pad, is too impractical for widespread use. For everything else, the fight continues. We build the strongest locks we can, knowing that someone somewhere is always trying to pick them. And that's okay. The goal is to make sure our locks are always just a little bit better, or take just a little bit longer to pick, than the value of what's inside.